Let's do an example problem calculating the calorimeter constant for a calorimeter. So the heat capacity of this calorimeter. Most students in their labs are going to be using a styrofoam cup for their calorimeter. It's just two styrofoam cups nesting. What you do to figure out the heat capacity of this, how much energy the system itself, these cups, how much energy they will absorb when the temperature increases, or how much energy they release when the temperature decreases inside the cup. Typically, you put your water, your solution in, and then you cover it with another cup, and you wait until you get a thermal equilibrium. So in this experiment, to determine the calorimeter constant, you're going to have cold water, and then you pour hot water into it. The graph, just so you can see this, on my example, and I just made this example up, okay? I said that I have a temperature of 70 degrees and 50 grams of water. That's hot, and I'm going to mix that with 40 grams of cold water that's at 40 degrees C. So I'd start with water in here that's at 40 degrees C. Honestly, you're going to use probably room temperature, 20 degrees C, something like that. So you have your cold water in the cup, you have that temperature, you have your hot water, take that temperature, pour it, stir it until they reach thermal equilibrium. The hot water decreases in temperature, it's exothermic, releasing its energy, and the cold water absorbs the energy, it's endothermic, until they reach that middle thermal equilibrium temperature of 53 degrees. So let's jump in and do this problem together. I first begin by labeling and writing down all of my data, a lot of data in these problems. So my hot water, of course, is water, and the reason why we use water on both of these, we know the specific heats, it's really easy. 4.184 joules per gram times degree C. I have a mass of 50 grams, initial temperature of 53, and that thermal equilibrium is 53 degrees. Now our cold water, again, specific heat 4.184 joules divided by gram times degree C, a mass of 40 grams, the temperature is 40 degrees C, and that thermal equilibrium is the 53 degrees C. Okay, now if you can do this next part, you've got calorimetry. It's what's releasing energy and then what absorbs that energy. Remember, we have a conservation of energy. The amount of energy released equals the amount of energy absorbed. Here is the equation. The amount of energy released by the hot water, that's the exothermic, the negative, is the same energy absorbed by the cold water and the calorimeter. So I'm going to pour hot water into this cold water. That energy goes two places. The energy from the hot water is going to go into the cold water and into the calorimeter. Now pause. You and I know a little bit of energy will be lost to the air. We will assume that that's negligible or non-existent, okay? We want to figure out how much energy is absorbed by this cup. What you do once you have this basic equation, and it will always be the same when you determine the calorimeter constant. Hot water releases energy, cold water and cup absorb the energy, your calorimeter. Break it into the formulas. We have Cm delta T for the hot, that's the exothermic negative, so important, remember that negative, equals the Cm delta T of the cold plus the calorimeter constant. That's your C-cal right there, times delta T. Now delta T, the change in temperature for the calorimeter, matches the cold water. It matches. It's going to be initially in thermal equilibrium with the cold water. So your delta T, I'm going to make a note of that, is from the cold water. And I also want to emphasize, if students make a mistake, they forget to mathematically include that negative. Make sure that you use that negative in your algebra. Okay, and then we just do a plug and chug. It's involved algebraic problem, but totally doable. So I start plugging in my C, 4.184 joules divided by gram times degree C, mass of the hot water, 50 grams, final minus initial. Final is 50, initial is 70. Notice when we subtract that, you get, actually I'll use this one, you get a negative 17. Negative times negative is positive. There's the importance of that negative. Equals the cold water, 4.184 joules divided by grams times degree C times the mass of the cold water, 40 times final, 53 minus 40. That gives me a difference of 13 degrees C, plus Here's my unknown. That's what we're trying to find, is the calorimeter constant, that heat capacity of these cups right here. And the temperature, initial or final minus initial, 53 minus that initial 40. So that's the 13 as well. Look at my units really quick. This is important. The grams are going to cancel, degrees C cancel, grams cancel, degrees C cancel, and here you're going to keep that 13 degrees C, okay? So I did my algebra. Notice we end up with joules equals joules plus the calorimeter constant times the degrees C. I'm going to subtract this over. I have the same unit. You know, when you add and subtract, we have to have the same unit. So I have the same unit. I get this 1380.72 joules equals the calorimeter constant times 13 degrees. Divide this over, check out my unit. Joules divided by degrees C. And that's the unit for our calorimeter constant. Come back to this. If this is in degrees C and this is joules divided by degrees C, multiply that. The degrees C cancel and you have joules plus joules. Perfect. So my calorimeter constant is 106 joules per degree C. Notice over here, I had two significant figures, and when I add, subtract my, my temperature, I'd have 2 sig figs. So everything's said and done, you end up with 2 sig figs. This will be 1.1 times 10 to the 2 joules divided by degrees C. Just so you know, when you're doing this in the lab, a reasonable calorimeter constant is anywhere between 30 and 300 joules per degree C for your styrofoam cups. Okay, great work. Enjoy being in the lab. If you're just doing practice problems, you will have this mastered. Remember, please like and subscribe to Old School Chemistry, and I'll see you next time. Thank you. Bye.